Okay, students, today we will be talking about the topic of extracting a minimum spanning tree from a graph. You know that if I have not told you earlier, but I remember I've told you earlier that a graph is also, rather a tree is also a graph. It means that the graph internally also contains a tree as well. For example, let me make a graph here. Now, if you see, this is a graph which has nodes and connecting edges, right? But let me draw a tree over it, which is basically underlying tree within this graph, but it's hidden, right? If you see here, this is a node, this is another node, and this is another node, right? So internally a graph also contains a tree, but or rather at times we say that a tree, now this is a tree is an acyclic graph, right? It means that a tree is basically a graph without having any cycles. Now if you see this blue colored graph, which is basically a tree, and if you see this red color graph, which is basically a graph itself, right? So this red color graph contains cycles, right? So it's not a tree, but here this is a graph, but it does not contain any cycles, so it is a tree as well. But if I draw an edge here, now if you see there is a cycle here, so it does not remain a tree anymore, it becomes a graph, right? So a tree is an acyclic graph. Now coming back to the original topic which we are supposed to cover, which is the minimum spanning trees. Now before going into the details of the minimum spanning tree, I am skipping a few slides. I will be coming back here. I just wanted to use a diagram. Now if you see here, this is a diagram. Now if you see, rather this is a graph. Now within this graph there are so many trees, right? For example, this can be regarded as a tree, right? This blue. Let me make another tree. For example, let me make a tree in green color. It will be upside down. Now if you see here, this green color is a tree as well, right? Now first of all, let me tell you the concept of a spanning tree. You recall from the earlier example that tree does not contain any cycle. Now if you see here, this tree which I have extracted from this graph does not contain any cycle. Now if I connect these two edges as well, now this results in a cycle, so it does not remain a tree anymore, it becomes a subgraph within this complete graph. Now but we want to extract a spanning tree. Now what is, let me try to hide this term. What is a spanning tree? A spanning tree is such a tree within the graph that it covers all the vertices or all the nodes within the tree. For example, let's say let me try to let me try to draw a fresh graph so that may be more visible to you, because drawing over the existing graph may distort some of the figures, right? Now if you see here, this is a graph. I want to extract a spanning tree from this graph, so I can extract many or multiple spanning trees from this graph, right? For example, these nodes are there, but I want to extract a tree that covers all the vertices within the graph, and of course we know that the tree will not have any cycles. Now if you see this this spanning tree, now this is one of the spanning tree. Let me try to make another spanning tree from this graph. Now if you see here, this is another spanning tree. let me try to draw another spanning tree here. Now this time I am going to make an incorrect spanning tree just to make sure that you understand how does it work. For example, now this is a wrong spanning tree because this tree does not is not contained within this graph. If you see this edge is not existing in this original graph, so that is why we cannot extract such kind of spanning tree. But if you see this blue graph, sorry, rather tree, now this is a spanning tree, this green is also a spanning tree. Now the spanning tree is a tree which connects all the vertices within the graph such that there is no cycle within the graph, right? Right. So there are a lot of applications of the extracting the spanning tree. Again, so far I have told you about the spanning tree. I have not told you about the minimum spanning tree, right? Shortly I will be telling you about the minimum spanning tree. Rather, it's now it's the time to tell you about the minimum spanning tree. I should not have rubbed that figure. Okay, let me redraw it. For example, this is the original graph, and this now for the sake of example, let me assign weights here as well. For example, this edge has a weight of 8, this edge has a weight of 7, this edge has a weight of, let's say, 2, and this edge has a weight of, let's say, 1, right? 1, right? So let me extract a spanning tree from this graph. There are multiple spanning tree as you saw in the earlier example. For example, now this spanning tree, and let me make another spanning tree which can be, for example, like this, right? Now if you see here, the cost of this spanning tree will be, for example, this cost of, okay, sorry, blue, cost of this edge is 8, this edge is so this was 7, this is 8, this is 1. So the total cost here is 16, right? But if we see here the cost, this cost of this edge is 7, the cost of this edge is 2, and this edge has cost 1. So the total cost of this spanning tree is 10. Now what does minimum spanning tree represents? The minimum spanning tree represents such graph, such tree which is extracted from the graph such that the sum of the weight of all the edges is minimum. So if we see here, this one has the minimum weight as compared to the blue one. So this is the minimum spanning tree, right? Can you think of any applications of extracting a minimum spanning tree from a graph? Is there any application? For example, one of the application is in electronics or circuits where we have a breadboard which contains so many holes, right? And we have to basically put some transistors or resistors here such that they get connected from the other equipment on the breadboard, and we need to connect these devices using a wire, right? So basically these nodes, these holes which are there, they represents they can be represented as nodes of the graph, and the connection, these wires, can be represented as an edge, right? So if we extract a minimum spanning tree for this breadboard example, so we will be having a spanning tree which will have minimum cost, right? And ultimately that tree will be used to put wires into this breadboard, which will result in much more less amount of wire being consumed for a breadboard, ultimately resulting in reduced cost, right? So that is the that is one of the utility of minimum spanning tree. Now if you see this definition here, which is quite simple, so the target of a minimum spanning tree is that sum of the weights of the graph edges which is extracted from the graph to form an MST should be minimum, right? Again, for example, another application is that that there are multiple cities. That there are multiple cities. Okay, I am trying to draw something, but yes, there are multiple cities in a country, and we want to connect. We want to make a road network between these multiple cities, such that the cost of constructing the road is minimized, and all of the cities gets connected as well. There a minimum spanning tree can be extracted to minimize the cost. So that is the utility of the minimum spanning trees. Now coming to the implementation of the algorithm which extracts the minimum spanning tree. Right now, one thing is that extracting, if we write an algorithm to extract the minimum spanning tree, the complexity of the algorithm will get exponential, right? So instead of writing an algorithm, we are going to write a heuristic which will be compromising on the optimality of the optimality aspect of the algorithms. So it will be producing a better solution, but it won't be the perfect, or it won't be the best solution, right? Because there can exist multiple spanning trees in a graph, right? So if we want to extract the best one, it is going to consume a lot of time, exponential amount of time. So, and we cannot afford it for real world graphs. Maybe this is small graph, so maybe for this we can extract multiple. For example, we say okay, this is a spanning tree, right? Maybe this one, and then we say okay, there can be another spanning tree as well, like maybe this one, right? Right. So, and we can extract a whole lot of a variety of spanning trees from the graph, but for a real world graph which may contain thousands and millions of nodes, extracting all possibilities is time consuming, right? And which results in exponential time. So there is a popular algorithm that is called Prim's algorithm. Remember, the word algorithm is placed here, but actually this is not an algorithm, this is a heuristic, right? Because it does not guarantee the optimal solution. It gives you the solution which may be, by chance it may be optimal, but most of the time it's a suboptimal solution, but acceptable enough to solve a given problem, right? Now this is the algorithm. First of all, I will be explaining the algorithm, then we will be doing a dry run of this algorithm, then you will be able to understand how it works. But let's first have a quick look of this algorithm, right? Now if you see here, the algorithm receives 3 parameters. The first one is the graph, the second one is the weight matrix which contains the edges of the weight, but if you are passing it the adjacency metric, this G attribute is enough. And the third one is the root, right? This root actually tells you about that from which point you would like to start growing your tree. For example, you may select this node as the starting point, then the tree will start growing from this point, right? But if you select maybe this point as the root, then the tree will start grow from this particular point, right? So this R parameter tells us about the root from where we need to start the constructing the minimum spanning tree. Now first of all, here we have a queue, and what we have done, we have placed all the vertices in the graph of the graph in this particular queue, right? Remember, this is a priority queue, right? It's not a simple queue, it is a priority queue. Now usually in a queue we have certain items. For example, this is an item, this is an item, this is an item, this is an item, and maybe this is an item, right? And this is the front of the queue, and this is the end of the queue, right? So if we want to remove an item, whosoever is in the front, he will or she will be removed, right? And then the next item will be removed, so on and so forth. But in a priority queue, the items are given priority based upon their various aspects, right? One of the various aspects, for example, if we give priority based upon height. Now when we have to extract someone from the queue, if we based upon a priority queue where priority is based upon height, then if you want to extract something, then the largest number will be extracted first. Then if you want to extract the next number, this one will be extracted, and then this one, and finally this one will be extracted, right? So here this is not a simple queue, this is a priority queue, right? And it is a min queue where the minimum item, like the least value, will be having the maximum priority. Right. Now here this loop executes and puts a value infinity in each and every node, right? And then this algorithm puts the key value 0 in the root node, right? And then it makes parent of the root node equals to null, right? Now, again I am explaining the code only at present, so you may feel like getting a bit confused, but shortly I will be explaining dry running the complete code. There you will be having a better understanding, but it is important to have the know-how of the code as well. Now once what we have done, we have put all the vertices in the queue, we have set keys of all the vertices to infinity, but we have set the key of the root node as 0 and parent of the root node as null, right? Then we execute a while loop, and this executes until the queue is not empty. What it does, it extracts the minimum value from the queue, right? And it calls it variable, it gives it or stores it in the variable u. And remember what we did, we put into all the nodes infinity as a key, and only root node had 0 value. So among all of these values, 0 was minimum, which was with the root, so obviously the root is going to be extracted here, right? Then what it does, it checks all the vertices which are adjacent to u and picks them one by one, right? And it checks if the vertex which it has picked is in the queue, and the weight between between u and v, right? This is u and this is v, right? Initially its weight will be 0, initially its weight will be infinity, there will be edge between them. For example, let us say value 7 is there, and we will see if weight of the edge between u and v is less than key of v, which is less than here, right? So what it will do, it will make p of v is equal to u, like this v's parent will become u, and the key value of v will become the weight, right? This will be removed and this weight 7 will come here, and then it will be picking rest of the neighbors as well, right? So this was a simple explanation of the code, but we need to execute it on the complete graph for multiple nodes to have a better understanding. So for that, let us consider this graph as an example. Now if you see here, initially we will be setting, now initially there are nodes which may contain any value here, right? So what we do by virtue of this loop, each node of the graph contains the key infinity, right. Then there comes the next line which assigns 0 value to the root node, right. So I think this will be root, and this you need to give in the input, but for this simulation this is, oh sorry, this one is the root, right. So here this 0 is assigned, right. Then this and the parent of this node will be null, right. Then we start a loop which will extract the minimum. Now if you see, obviously the minimum value is this one, right. So this will be extracted from the queue. Now this is now visually what we have done here, the node which is getting or which gets extracted from the queue is marked using a black outline, so that it is obvious to you, and the rest of the nodes which are presently in the queue are marked with the light blue color. Now what it will do, it will now pick its neighbors. One of its neighbor is this node, right, and the other neighbor is this node, right. So what it will do, it will then it can pick the neighbors in any order, right. So let us consider this neighbor first. Now it will see that the weight between these two is 14, which is less than infinity. So it will do what? It will remove infinity from here, it will place 14 here, and then it will remove, it will see that the weight between these two nodes is 3, which is less than infinity. So it will be replacing this infinity with 3. Now remember, it is only considering its neighboring node, but these neighboring node are not extracted from the queue yet, no, right. So let me see that it works or not. So if you see here, this weight is updated and this weight will also be updated, right. And if you see the arrow sign, this arrow sign basically indicates the parent relationship, right. Now from the remaining of the nodes, it will do what? It will extract the minimum value. Now if you see here, the minimum value is 3, right. Now this will be extracted. See, now what will happen? It will check this neighbor. The neighbor of 3 is this node as well, but this 0, this one is also the neighbor of 3, but if you see here, this is already marked using black outline. It means that this neighbor has already been extracted from the queue. Now this condition will be false right here. So we will be considering only these two neighbors. Now let us consider this one first. If you see here, 8 is less than infinity, so we will be placing 8 here, and if you see here, 10 is less than 14, so this 14 will get removed, and here we will have 10, right. Now this is how it happens, right, and the parents, if you see here, parents also gets updated, right. Now in the remaining of the graph, all the nodes which are now in the queue, because this is extracted from the queue, this is extracted from the queue, in the remaining the minimum value is 8, right. So we will be going with 8. Now the neighbors of 8 which are in the queue, 3 is also the neighbor, but it is not in the queue anymore. So this neighbor and this neighbor will be considered. Now if you see here, 15 is less than infinity, so here we will have 15, and 2 is less than infinity, so here we will have 2, right. So this is how, and parents will be updated as well. Now this is 2 and this is 18. Now in the remaining of the graph, the nodes which are in the queue, minimum key will be extracted. Now this is the minimum key. Now this gets extracted. Now its neighbor which are in the queue, if we see here, this neighbor is in the queue, this neighbor is in the queue, and this neighbor is in the queue here, right. Now if you see here, 9 is less than infinity, so this value will get 9. If you see here, 4 is less than infinity, so this node will get value 4, and here as it gets 9, this parent relationship will be like this, right. And here as it gets 4, it will be like this, and 5 is less than 10, so this 10 will be replaced by 5, and it will become a parent like this, right. Now let's see what happens. This gets updated, this gets updated, and this node gets updated. Now in the remaining 4 nodes which are in the graph, these 4 nodes which are in the graph, the minimum value is this one, right. So we will be extracting this. It only has one neighbor which is in the queue, Now we will see that the edge between these two nodes has a minimum value. So if we see a 6 which is not less than 5, so it is not going to get updated, right. So neither this 6 will come here, nor the parent relationship will be created, because the edge weight on the edge is greater, right. So nothing happens. But in the remaining graph, these 3 nodes are there. So minimum value is this one. So the next next turn is for the node 5. This 5 will get extracted from the queue, but it has no node. If you see here, it has no node which is placed inside the queue, so nothing will happen, right. Then among the 2 nodes which are in the graph, which are in the queue, this 9 has a minimum value, it will get extracted, but as was the case for with 5, this also has no node which is in the queue, so nothing more will happen, and same goes for 15 as well. So now if you pick this graph from this point, this is a minimum spanning tree which is in the graph. Remember, this is not the best minimum spanning tree. You can maybe manually extract, because it is a very tiny graph. You may get a different spanning tree, but that is why I am telling you that this is not an algorithm, this is a heuristic. But again, this is a popular heuristic which works. And one thing to notice as well, because we started our algorithm from this point, maybe if we start rather for sure, if we start our algorithm from this point, we will get a totally different minimum spanning tree, right. So this is how Prim's algorithm works. There are certain hidden costs in the Prim algorithm, because if we see here, this line when it executes, it does not work in simple order of one time. It actually has a lot of processing underneath it, so it will also consume some time. So that is the hidden cost within the Prim's algorithm. But again, I hope you have got a good idea, adequate idea of how Prim's algorithm works.